Okay, so let me thank you for attending this webinar. I will be, as Orla explained, I will be talking about the extended stellar parameterizer for ultra-cool dwarfs module that produces astrophysical parameters for, as the name says, ultra-cool dwarfs. Ultra-cool dwarfs are the end of the main sequence. They were introduced by David Kirkpatrick in 1997, and in principle, they include sources in the main sequence or younger of spectral types M7 or later. This is a diagram of this the main sequence in the H band from B0 to Y0. Ultra-cool dwarfs would be at the bottom right corner of this color absolute magnitude diagram. Just a brief reminder of what you can see in this box called UCDs, ultra-cool dwarfs. You have L dwarfs that show absorption features in their spectra due to hydrides and neutral alkali elements. And this is what we have actually in the spectra recorded by Gaia. Then we have at the LT transition, we have cloud clearing and the onset of methane opacity, which causes, as you will see in some of the plots I will show you later, color trend reversal. In general, as you go to later spectral types and cooler sources, you have redder color. That's what we all expect. But at some point, due to the chemistry and the emergence of clouds in their atmospheres, you see that suddenly that after the LT transitions, the colors get bluer for cooler objects as opposed to the general trend. And then I point out that there are a couple of elements that are important in interpreting the spectra of these ultra-cool dwarfs. One of them is disequilibrium chemistry and the vertical transport of species. And also that the mismatch between theoretical spectra and observations is telling us that we have non-adiabatic pressure temperature profiles in these sources. Now, precedents in Gaia, this is not the DR3 catalog of ultra-cool dwarfs, and the products related to ultra-cool dwarfs in DR3 are not the first in the run of Gaia. In 2017, Smart et al. Produced the first Gaia ultra-cool dwarf sample, which comprised ultra-cool dwarfs well known from the literature that were cross-matched to the first data release. They are shown in the leftmost plot as blue, green, and red circles for ML and T ultra-cool dwarfs, superimposed on the DR2 color absolute magnitude diagram by Karim Babusio et al. In 2018. So you can see this is the main sequence, and ultra-cool dwarfs are at the bottom faint red end of the main sequence. Then also in data release 2, Céline Rail produced a catalog of ultra-cool dwarfs of 13,000 ultra-cool dwarfs, again defined as spectral types M7 or later. But you have to remember that in data release 2, as in early data release 3, there were no spectra published. They were not available. So the selection criteria had to be very conservative to avoid contamination by spurious parallaxes, for example. So hence the number 13,000. Then in the Gaia early data release 3, sorry, there is a missing E in the rightmost plot. There should be an E there. The Gaia catalog of nearby stars contain 2,880 and 79 additional candidates compared to the catalog by Céline. Mostly of the M and L spectral types. Now, these are the three precedents in the history of Gaia, so to speak. And in data release 3, the APSIS produced a catalog of ultra-cool dwarfs, which comprises roughly 94,000 candidates, new candidates, to be compared with the 13,000 produced in DR2. I show you here three color absolute magnitude diagrams produced by naive inversion of the parallax. There is no distance inference here in this plot. We just invert the parallax to get something which we hope is related to the distance. The top row shows you all 94,000 sources, as I said, in three color absolute magnitude diagrams, G minus RP in the left, so that is all Gaia magnitudes, G minus J in the middle plots, and J is the two mass band, and G minus Y's W1 in the rightmost column. And the difference between the two rows is in the first one, you have all 94,000 candidates. In the bottom row, we only select those that have the best quality flags in the two mass and Y's photometry. Things to note, if you look at the rightmost column, you see the reversal in the color trend at the LT transition. The coolest UCDs become bluer, and there is a spread. The gray shade in the background is a kernel density estimate of the UCDs in this diagram, and you see there are some spread to the right to redder colors, which is due to known and understood contamination by nearby sources in the spectral window from which we extract the RP spectrum, which causes contamination in the RP flux, and hence this artificial reddening of the sources. There is a plume at the top of our catalog, and this is due to star-forming regions and young clusters in the neighborhood of the sun. These ultra-cool dwarfs in these young stellar regions are brighter. We know they're younger, hotter, and brighter. And so they appear in our catalog as this plume above. We will see more about them in later transparencies. Now, I'll try to explain what we did, because that actually explains what's in there in the UCD catalog. First of all, the way these modules work is there is a first selection of sources. Of course, the number of Gaia sources is very large. And so first thing, we select those that will be processed. And by processing, we understand the production of astrophysical parameters from the Gaia data. Now, in order to do the selection, of course, not every Gaia source is a candidate to a UCD. We use 4 Gaia observations, which are the parallax, the G and RP band magnitudes, and the continuous representation of the internally calibrated, in this case, RP spectra, in terms of coefficients. As you know, the Gaia spectra, in particular the RP spectra, come as coefficients of the decomposition of the spectrum in a given orthonormal basis. So we use this representation, these 51 coefficients, to reconstruct the RP spectrum, and we imposed these criteria here, which I will explain. The first one is we select sources that are nearby with a parallax greater than 1.7 milliarc seconds, which is the parallax at which the brightest UCD would be seen with the Gaia limiting magnitude, nominal limiting magnitude. So that is the farthest we could see an ultra-cool dwarf of type M7 with a very low surface gravity due to youth. Now we require that the color index G minus GRP is rather than 1 magnitude. which actually kind of separates ultra-cool dwarfs from white dwarfs in the color absolute magnitude diagram. And then we require that the RP spectrum is red, is relatively red. And we do this by imposing that the quantiles of the flux distribution in the RP band are redder than some limits in pseudopixel space. We require that the pixel at which we attain 33% of the total RP flux is greater than 60. I'm showing these values for one spectrum. On the right, this would be the spectrum of, say, M7 source. So this would be the limit of the definition of an ultra-cool dwarf. So to speak, the hottest and bluest RP spectrum that we can see in our catalog. And red shows the pseudopixel at which we attain 33% of the total flux. The spectrum that you see here is normalized such that the total flux is 1. So 33% is to the left of the red line. And green is the median, the point at which we attain 50% of the total flux. So there is the same flux to the left and to the right of the green line. And then 67%, 67 percentile of the RP spectrum is denoted by the blue line. So we basically we look at well-known UCDs in the Gaia ultra-cool dwarf sample gathered by Ricky Smart in 2017. We see what's the distribution of these percentiles for the sample, and we define some margin, security margin, which explains why the ESP-UCD module is actually processing sources hotter than the limit, but okay, we can filter them out in later stages. So these are the sources that we select in order to produce astrophysical parameters, okay? But it doesn't mean that all these sources that fulfill this criteria are actually UCDs, but this is a first selection to make manageable the data processing. Then we do, as you know, in DR3, not all RP spectra are published. There were some decisions taken as to what RP spectra were published. And in ESP-UCD, we suggested to be somehow liberal. There are RP spectra of UCDs published that do not match the quality criteria of the rest of DR3. But of course, if we apply the same criteria as for the rest of DR3, there would be probably no RP spectrum published, or very few spectra published. So basically, these are the criteria for AP publication. We publish sources with an Euclidean distance to a set of training templates greater than some threshold, which is minus 2.05. So we had a set of training templates. I'll come back to this later, of real ultra-cool dwarfs observed by Gaia. These were our templates, and we required that the Euclidean distance between the spectra of a candidate and these templates was reasonably small. Also, that the number of transits used to construct the RP spectrum was less than 15, that the effective temperature produced by our module was in the range between 500 and 2700 Kelvin. We also required that the normalized RP spectrum had a median curvature of less than 10 times to the minus 5. As you probably know, there are the transformation from the basis coefficients into an RP spectrum, flux versus wavelength. For the lower quality RP spectrum, produces wiggles, oscillations, high frequency oscillations, high in the context of RP spectra. So we wanted to publish only RP spectra which were not severely affected by these oscillations. So this is this criterion. but avoids spectra with high median curvature. Now, the sum of the normalized RP spectrum fluxes below the zero flux level, you may know that you can get some RP spectra with, of course, negative values of the flux. This is understood in terms of data reduction, continuum subtraction, etc. But we require that in this normalized version of the RP spectrum, where the sum of the fluxes was 1, we require that the fraction of sources with negative fluxes was less than 10%. Also, visual inspection of our candidates revealed that there are many with reddest flux. So if you look at the reddest wavelength sampled by the RP spectrum, some of them had a lot of flux where the sensitivity of the RP spectrograph and plus CCD was very low. So it is not expected that at the reddest wavelength you have a significant flux. So in order to remove that source of poor quality RP spectra, we require that this reddest flux was lower than 0.015. And finally, we required sources that fulfill this condition here. It is represented by this continuous line. In the diagram, it shows the parallax in the x-axis, logarithm of the parallax in the x-axis, and logarithm of the uncertainty of the parallax in the y-axis. And after we applied many of these quality criteria, we realized there were 2 overdensities in this diagram, and the good quality sources were below this continuous line. Of course, across the line, there is a mixture of good and bad spectra, and we expect to refine these criteria in future releases. Now, after processing the sources selected with these criteria, we carried out a post-processing. During the preparation of data release 3, we worked with two regression modules, 2 modules that produce effective temperatures from the RP spectra. And we realized that in the hotter regime, above 2500 Kelvin, there was a discrepancy between the two. Of course, the 2 of them do not coincide. They produce relatively different prediction of effective temperature. But above 2500, the difference were systematic and significant. And we compare the predictions with Sloan, Simbad. We look at the Gaia ultracooled dwarf sample by Ricky Smart, and we got the impression that our temperatures were overestimated. So we applied a correction to bring the 2 together, the two predictions together. I'll explain later what these 2 predictions are. And so we did this calibration in the hot regime, and we inflated the uncertainties by a factor of 7, which we derived again from comparisons for our golden sample, which is the Gaia ultracooled dwarf sample. Again, I repeat, these are ultracooled dwarfs known before the launch of Gaia, well-known ultracooled dwarfs, for which there is at least an estimate of the spectral time. Now, what does the, other than the selection of candidate, what does the ultracooled dwarf module do? It does predict astrophysical parameters for ultracooled dwarfs based on the RP spectrum. Now, ideally, the original objectives were to produce effective temperatures, gravities, and metallicities for these sources. Unfortunately, we have been unable to produce reliable estimates of gravity, surface gravity, and metallicity. And I'll explain you why. This figure, I show you the x-axis is the wavelength, the y-axis is the normalized transmission for the 3 bands of Gaia. In blue, it's BP. In red, it's RP. In orange, it's the G-band transmission. And superimposed on that, I show the 2 spectra of an L0 and an L6 ultracooled dwarf. This figure is taken from the paper by Ricky Smart that presents the Gaia ultracooled dwarf sample, and it shows you that actually the RP spectrum is just the blue tail of the spectral energy distribution of these sources. Right? The vast majority of the flux emitted in the SED of ultracooled dwarfs is in the infrared, near, mid, or far infrared. And the RP wavelength range is only a tiny fraction of the total spectral energy distribution. So these are very faint sources and very red sources. And RP is obviously not an optimal instrument to study these sources. So these absorption features that you see here are due to hydrides, and there are some narrow lines of alkali elements. These will be translated into the spectral features that we see in the RP spectrum. This is a compilation of observed RP spectra on BT settle models that show a very significant discrepancy between the BT settle models shown in blue on the spectral standards and the median spectra shown in red and black. The black lines are hardly visible because they are covered by the red lines, which are the templates. So just look from M8, M9. M9, the discrepancy is already significant between the blue and red line. The blue is the BT settle model. And this discrepancy gets more and more significant. This is an L3 or L4. You see that there is a big difference. There's a dip here. These are absorption features that are present in the Gaia RP spectra, and of which there is no trace in the blue BT settle models. And then by the spectral type L7, L8, we recover the consistency between models and observations. So this means that BT settle models, unfortunately, are not a good tool to predict astrophysical parameters from RP spectra. This happens as well for other synthetic family models. So we were left without our main tool to predict astrophysical parameters, especially gravity, surface gravity, and metallicity. I'll explain later what we did to circumvent this problem for temperature, but there was no way we could actually produce consistent prediction for the other two astrophysical parameters, gravity and metallicity, without synthetic models that reproduced reasonably well the observed spectrum. Now, one important thing to bear in mind is that we were the only module in APSIS that actually carried out truncation of the coefficient of the wave the spectrum coefficients to produce the RP spectrum. Remember, spectra come in the form of projections onto an orthonormal basis, 51 coefficients, if I recall correctly. We didn't use the 51 coefficients to produce the RP spectrum. We removed coefficients which were not significantly larger than their uncertainties. We did some kind of noise reduction by using a rule which could resemble the 3 sigma detection criterion, which is so often used in science, right? So we used all the procedure is explained in Carrasco et al. 2021. There is one parameter for this reconstruction of the spectra, which is A, and we fixed A equal to 3 in equation 27 of this paper. So this was done in order to reduce the spurious oscillations, high frequency oscillation that I was discussing before, the wiggles in the RP spectrum. Now, this is a repetition of something I said before. Both the selection criteria for processing and the criteria for publication of the RP spectra in DR3 are based on the same proxies, on the same quality criteria. Only for publication of the RP spectra, we were a bit more restrictive than for processing. Okay, but basically it's more or less the same. The curvature, the negative fraction, the flux in the reddest pixel, number of observations, etc., etc., and the distance to the templates. Now, what we did to circumvent the problem of the mismatch between the synthetic spectra and the observed spectra of UCDs is to construct an empirical training set. We could do that for effective temperature because we have a large enough set of Gaia templates for which we have either temperature estimates from spectroscopy or at least spectral types. Okay, so but this is not the case for surface gravity or metallicity. We not only we need a sufficiently large set, we also need the set of examples to cover homogeneously and densely the space of parameters. So we need enough examples for all values of metallicity, for all values of gravity. And unfortunately, that is not so often the case. However, for temperature, we do have many spectral types, at least, if not temperatures. Now, what we did was we actually transformed the RP spectra into a space of coordinates, which you can think of as principal components. It's not principal components. The foundations of principal components are useless in this context. This is a nonlinear projection of the RP spectra, which contains, in our case, contained 120 flux values, into a lower dimensional space where proximity in this new space reflects proximity in the RP spectrum, in the full RP spectrum. Now, on the left-hand side plot, we have these new coordinates. This would be the diffusion map coordinate 1 versus diffusion map coordinate 2. Diffusion maps is the projection technique that we used. And you see that the points that represent RP spectra, each point here represents an RP spectrum. In the red circles represent our templates, and the black dots represent, actual RP spectra of sources which have no effective temperature attached from spectral types from the literature. So we selected good quality RP spectra without an effective temperature attached, and we constructed this map. You see there is a wiggle here. Most of the diffusion map is rather smooth. It's nice, so temperature goes along the parameter lambda, which parameterizes this curve. Here we have this wiggle where a significant change in effective temperature of several hundred Kelvin results in hardly no change or very, very, very subtle changes in the RP spectrum. We see this wiggle here just because we selected the best quality RP spectra. Remember, the circles are the templates and the black dots are true RP spectra of relatively bright UCDs. That's why we can see this wiggle. Okay, so what we did was we used the templates to calibrate temperature along this curve. Remember, the circles are the templates. We can use the templates to attach an effective temperature to each point along the curve. This is what you see in the rightmost panel. We have black dots are the templates here, and the orange squares, small squares, are the Gaia ultra-cooled dwarf sample, but not the standard, not the templates, but the rest of UCDs. You see there is significant dispersion in the non-standards, but the black dots show relatively narrow sequence, which is followed by the blue line. So we use these to construct a set of several hundred UCDs, true, real Gaia UCD spectra, for which we had estimates of the temperature using this calibration. And it was that set of several hundred spectra that we used for training our regression model. Now, once we did that, we produced quality flags for our effective temperature predictions. And you can see here the distribution in the sky of class 0, which is the best quality, class 1 and class 2 sources. And the two most important things to remark here is you can see over densities in the celestial sphere. Here the color code reflects the reciprocal of the parallax, so it's a proxy for distance. You see these over densities, which you can imagine correspond to star-forming regions and clusters. And you see an over density in the poorest quality class at the galactic plane and near the bulge. I'll come back to this later. That is the first flag, the quality class 0, 1, or 2. There is a second flag which marks inconsistencies in the color absolute magnitude positions. You can see in the right-hand side a color absolute magnitude, Gaia color absolute magnitude diagram. This is a full set of 94,000 UCD candidates published in DR3, and the black squares corresponds to sources which have too cool a temperature for their position in the HR diagram. And this can be due to two things. We looked in SIMBAD at these sources. Of course, not all of them have entries in SIMBAD, but there was a significant fraction of them with flags indicating youth. It would be all those that are above the main sequence. The main sequence would run here at the lower envelope of this diagram. These sources are bright and redder, and you will see later that they are consistent with being young, belonging to some of these star-forming regions or clusters. And some of them had hints of poor quality in the RP spectrum. So it's a mixture. If you look here, this is the celestial map, longitude versus latitude. And this concentration here is clearly a star-forming region. This one here as well, it's Taurus, Orion. But this concentration here around the bulge and in the galactic plane, this is due to reddening. So it's a mixture of the two, okay? Now the UCD catalog, as I said, contains 3 quality classes, and this is the distribution as a function of temperature. Gray, green, and blue mark the 3 quality classes. The most numerous is quality 0, and it's roughly 50% of the 94,000. And then the other 2 quality classes, quality class 1 and 2, would be 25% each. I'm rounding off, okay? And this is the distribution of the parallax versus the G magnitude, with the color code reflecting the effective temperature. And you can see these vertical stripes here, which correspond to the star-forming regions. So they are all more or less at the same distance, heliocentric distance. So this is why they appear as a vertical stripe, same parallax. And those one here as well. And you can see the coolest end of the main sequence as visible by Gaia, which goes down to the spectral types T, but only a handful of them. This would be L, the L region from yellow to blue would be the L sequence. Now we did validation, of course, it's difficult to do validation here. There is not much more we can do other than comparing our effective temperature predictions with the spectral types in the literature. Of course, also with the temperature for those sources that have high resolution spectra and high resolution determinations of the astrophysical parameters. And a comparison, so this is the comparison of our prediction of effective temperature here on the y-axis. This is the ESP-UCD prediction on the y-axis. This is the effective temperature that we derive from the GUCDS spectral types using calibration by Stephens et al. Okay, so you see the difficulty, and you see that when you use a spectral type, the dispersion, the scatter of sources is not narrow. But also we have indications that these spectral types, of course, are a mixture of many papers in the literature with different criteria. We have mixture there. We have inhomogeneities, inconsistencies, which I think we are on the way to solve for DR4. So we will work with an improved golden standard from UCDs. This is the comparison of our effective temperatures with the SIMBAD spectral type. And these are the calibrations in red and blue from Stephens et al. In red, we have calibration using optical spectra, optical spectral types, and in blue, using infrared spectral types. As you can see, we can go down to mid-T, but it's only for maybe one case in each spectral type beam.
Sorry, Luis, just a check with the type. It's 1245 at the moment.
45.
Just
okay,
for
I'll try to go. Yeah. Okay.
No, so, don't worry about it.
Okay, so again, this is the distribution of the sources of the 94,000 sources in the sky. Quality classes 0 and 1. Quality class 2, you see that the contamination due to extinction near the galactic plane is mostly concentrated in class 2. We did a clustering analysis looking for concentrate over densities in the space of parallaxes, proper motions, and celestial coordinates. So it's not only celestial coordinates here in the lower left plot. It's a combination of, as I said, parallaxes, proper motions, and celestial coordinates. We define a series of groups. There they are almost all identified with previously known star-forming regions and clusters. Of course, Gaia has produced a large, vast set of new clusters in the neighborhood of the sun. There were some residual overdensities that one could saw in the celestial sphere projection, but these are not associated to concentrations in parallax or proper motions. They only become apparent in celestial coordinates, and they coincide with some star-forming regions. I'll explain this later. Now, when we look at the color absolute magnitude diagram of these overdensities, we see that they are all above the main sequence. So the color sequence is the main sequence. We are only plotting here the best quality. And the sources in these overdensities, they all fall above the main sequence, and they are clearly above for the most young star-forming regions like Rho Ophiuchus, Upper Crux, and as you go older, the Pleiades almost mixes perfectly well with the main sequence. Okay, so we had a clear indication of youth here in the color absolute magnitude diagram. If we look at the RP spectra, we see that the younger the star-forming region, the less pronounced were the absorption features. So you see here that the youngest regions, Rho Ophiuchus, NGC 1333, IC 348, Orion, Serpens, these are all below 10 mega years. They show less conspicuous absorption features in their RP spectra. The black line would be the median RP spectrum in the main sequence. Okay, so these are all sources, as I showed you before, these are all sources clearly above, brighter than one would expect from the main sequence. And you see difference in the RP spectrum. This is the plot for the 2500 Kelvin beam, but there are equivalent plots for other temperatures. Now, if you recall, there were some overdensities left in the celestial sphere projection, which were not associated to typical proper motions or parallaxes, and they coincided with the position of some star-forming regions. And we looked deeper into these overdensities, trying to understand what they were, and it turns out that they are background sources. If we actually look at these sources and retrieve their maximum absorption extinction along the line of sight from the Planck maps, and we try to see where these sources would be if we corrected for this maximum line of sight extinction. We see these sources would be red and blue in this diagram, in this color absolute magnitude diagram. This is what we see, and the green and orange points are where they would lie if we corrected for this maximum line of sight absorption. And of course, the maximum line of sight absorption needs to not be the true absorption. But if we do that, you see that the position of the sources is consistent with being earlier type M type stars or late K along the main sequence. The black dots are the Gaia catalog of nearby stars sources. And you see that, so the explanation for these residual overdensities is they are background objects behind the star-forming regions, which due to reddening enter the domain or that appears to be UCDs. They are not UCDs, but they look like, their RP spectra actually look like UCDs, but they are not. Okay, so there is contamination in the 94,000 catalog of UCD. There's contamination by background sources, which we will try to flag in subsequent releases. I'm finishing here. This is also two plots. You have available the full DR3 catalog. You can cross-match the results from the ESP-UCD catalog with the other parts of the Gaia archive. In this case, we cross-match that with the results from CU7, which marks, studies, analyzes, characterizes variability. And we see that we have several, a few tens of variable UCDs. These are the orange dots in the rightmost plot. This is color absolute magnitude. All orange dots are variable. If you look in the left, you have the difference between the mean and the median G magnitude, which is telling you how asymmetric is the light curve versus the actual G magnitude measured by Gaia. And you see that most of the sources are aligned with 0, meaning that they have relatively symmetric time series. So you have something which would resemble either random noise or sinusoidal variations. But then you have outliers to the left and to the right. The vertical bars show you the range of G magnitudes in the time series, and the circles marks the median. So the left-hand outliers, they are sources which have a median down below the bar and have some bright outliers. So this would resemble something like flares. You have a time series with a relatively constant flux, and then a few values which are clearly above the median. And on the right-hand side, you have the opposite behavior. You have outliers which are significantly fainter than the median, and this could be interpreted as circum-UCD material passing in front of us in the line of sight, or eclipses, or but of course more work would be needed here. So there is a wealth of information here that you can use to analyze and further study. This is the end of the presentation. Thank you very much.